If complex numbers are these geometrical things, then why are they even numbers? I mean, what makes a number a number? And the answer to that is kind of simple. You can add numbers, you can multiply numbers, you can divide them, you can do all these operations, but so far you've not been able to do this with shapes. What has to be realized at this point is that complex numbers are just vectors. Either they're defined as a length and an angle as in the polar representation, or by two coordinates as in the rectangular representation. It's still a vector, something with a magnitude and a direction. It's like an arrow. But how do we add arrows? You take the first arrow as it is, and you put the tail of the second arrow right next to the head of the first arrow. Then you draw a new arrow from the tail of the first arrow to the head of the second arrow. Using numbers, you simply add up the coordinates. So you add up the real part, which is A, and you add up the imaginary part, which is IB, separately. So you form a parallelogram. And subtraction is just as simple. For that, you have to realize that subtracting something is equal to adding a negative thing. 10 minus 3 is equal to 10 plus minus 3. Vector plus vector is equal to vector plus minus vector. What is a minus vector? That's easy. We have established in the middle of this lecture that turning something around by 180 degrees is exactly equal to multiplying it by minus 1. So minus vector is just the backwards vector. So what you do is you add the coordinates of the backwards vector. The real power of this, and the understanding that they don't teach you usually in schools, that here the difference between vectors, numbers, and shapes is starting to break down. And now you have something more unified, something that's just maths. And the notions of addition and subtraction are also getting extended beyond the things that you were taught in elementary school. It's not counting on your fingers anymore. And that is the general progression in the language of math. Things are getting extended so that they can encompass more meaning. Multiplication is a bit more complicated than addition and subtraction. Moreover, division is not just going to be the same thing as multiplication. We need to define additional things. In rectangular form, multiplication is not that hard. All you have to realize is that a complex number has two parts. It's the same thing as having two terms. And why is that? It's because they are separated by a plus sign. So if you take two numbers with two terms, you're going to end up with 4. Here is what it is. First, you multiply the firsts. That's the real parts. Then you do the inners, the imaginary times the real. Then the outers, real times imaginary. And finally, the lasts, imaginary times imaginary. In this one, you have to remember that I times I is minus 1. So you're going to get an extra negative sign, but a real number. Not necessarily a negative number, because it might be negative to start with, and then you get a positive number. And finally, you sum up the real and the imaginary parts, which gives you a new complex number. Wasn't so hard, was it? But now I'm going to show you the easier way, and that is to use the polar representation. All you need is the length, which is called the modulus. I don't know if I actually told you it's called the modulus, but now I'm telling you the length of the complex number vector, that's called the modulus. And the other thing you need is the orientation, and that's noted as e to the I phi. And modulus is just a, it's just a number. So now you've got a to the I phi, you've got 2 of this type of number. All you do is multiply them, literally just multiply. Consequently, the vector lengths are going to multiply, but something else is happening to the exponential parts, because when you multiply e to the I something, then you have to add up the exponents, and as a result, the angles will add. So multiply the modulus, add up the angle. Shrink and turn, or grow and turn. But shrink and turn just sounds better. That was multiplication, but how about repeated multiplication? It's also called exponentiation. What happens if you raise the complex number z to the power of n? The modulus is just obvious because it is simply exponentiated. And we also know what happens to the angles. They are added over and over again. What is that? That's just multiplication. So the angles are going to be multiplied by n instead of being exponentiated by n. But if this is not satisfactory, then here is a more rigorous mathematical proof. Start with Euler's formula and then just exponentiate the exponential. And of course, by laws of easy mathematics, you know that it's just multiplying the x by n. Apply Euler's formula again, and now you see that n times x is the angle. An interesting or maybe boring fact about this formula, de Moivre's formula, is that it was not invented by Mr. de Moivre. We don't know where it came from, but it could have come from anybody. It's pretty easy math.